So in this problem we're being asked to determine the angular velocity and acceleration of this link BC and the speed and the acceleration of this piston C. And what's going on in this problem is that this wheel, we'll call it AB, is rotating clockwise at a speed of 6 radians per second and an angular acceleration of 3 radians per second squared. And what that does is pushes this linkage BC to the right and pushes the piston C to the upper right at a 30-degree angle. Let's start by looking at the velocity of C, and I know the velocity of C is equal to the velocity of B plus the velocity of C with respect to B. And what's interesting is that the velocity of C with respect to B is only rotational. So if we rode along, essentially if the camera followed B, or if we were able to ride on this linkage B, we would find that this linkage BC can only rotate, it cannot translate with respect to this pin B. So what that means is I can change the velocity VCB into a rotational component, which is omega BC crossed with the position of C with respect to B. So let's plug in numbers. What I'll have is the velocity of B is equal to this 0.2 meters times 6 radians per second in the I hat direction. So point B is moving only to the right simply because it's directly above point A. We don't know omega BC yet, but we do know it acts in the k hat direction, or out of the screen. So I'll just write omega BC times k hat. And we're going to cross this with 0.8 meters in the I hat direction, which is the position of C with respect to B. So what I'll come up with then is 1.2 meters per second in the I hat direction. And when I cross k hat with I hat, what I'll get is a positive j hat direction if we're using right-hand coordinate axes, which we are. So that means for the j hat term, I'll get 0.8 times omega BC in the j hat direction. Now there's also a constraint here in that piston C can only move to the upper right at an angle 30 degrees above the horizontal. So what I can say is that the velocity, the magnitude, or the speed of C, the magnitude of the velocity is equal to Vc cosine 30 in the I hat direction plus Vc times the sine of 30 in the j hat direction. And ultimately what I have are two equations and two unknowns. My two equations are in the I and j hat direction, and my two unknowns are omega BC and Vc. So let's write the I hat components of these equations, and what I'll get is 1.2 meters per second, and that's going to equal Vc times the cosine of 30. And in the j hat direction I'll have 0.8 omega BC, and that will equal Vc times the sine of 30. And solving these two equations, what I'll come up with is Vc is equal to 1.39 meters per second, and omega BC, the angular velocity of linkage BC, is equal to 0.866 radians per second. One thing to note is that the angular velocity is positive, and positive means a counterclockwise rotation. And if I drew point B here, if I drew it a second later, it would be located there, and point C would be located at that point. And if I connected these two with a new line, what I see is that linkage BC actually rotated a little bit in the counterclockwise direction. So my positive value for omega BC it sounds reasonable. So I've cleaned up the equations and moved the answer to the upper right because we're going to need that for the second part of the problem, where we find the acceleration and the angular velocity, or the angular acceleration of link BC. So just like I did with the velocity, I can say that the acceleration of point C is equal to the acceleration of point B plus the acceleration of point C with respect to B. And again, if we rode along, if we were able to follow pivot B, we would see that the rotation is only rotational. The velocity is only rotational. So I can rewrite this we've got the acceleration of B again, but now we've got both centripetal acceleration and tangential acceleration. And the tangential acceleration is, we'll add this in, is equal to alpha BC crossed with the position of C with respect to B. And the centripetal acceleration is equal to negative omega BC squared, it's acting in the negative direction, times the position of C with respect to B. And again, there's this constraint that location C, or piston C, can only accelerate to the upper right. And I can write the acceleration of C is equal to the magnitude of the acceleration of C times the cosine of 30, and that's in the I hat direction, plus, again, the magnitude of the acceleration of C times the sine of 30, and that's acting in the j hat direction. So let me eliminate this intermediate equation so that we can see more clearly what's going on. And the next thing I need to find is the acceleration of pin B. And it's going to have some centripetal acceleration in the negative j hat direction, but it's also going to have some tangential acceleration because the wheel has an angular acceleration associated with it. So I can say the acceleration of B is equal to alpha of that wheel crossed with the position of B with respect to A, and that's my tangential acceleration. My centripetal acceleration is negative omega squared times the position of B with respect to A. Plugging in numbers, my angular acceleration is negative 3 radians per second squared in the k-hat direction. It's negative because this is accelerating clockwise, and I'm using a right-hand coordinate axis. And I'll cross that, the position of B with respect to A. I move from A to B, so I move up 0.2 meters in the j-hat direction, minus omega squared is 6 radians per second, times again the position of B with respect to A. Doing the arithmetic, what I have, the acceleration of B, the tangential component is 0.6 meters per second squared, and the centripetal component acting downward is 7.2 meters per second squared. So I figured out the acceleration of B. Let's figure out the angular velocity of BC crossed with the position of C with respect to B. And that'll equal alpha BC in the k-hat direction. We don't know alpha BC yet. We'll solve for it. Crossed with the position of C now with respect to B, so we go from B to C, so we move to the right 0.8 meters in the I-hat direction. And again, K crossed with I gives me something in the positive J-hat direction, so what I'll come up with is 0.8 alpha BC in the J-hat direction. So we know this term, and finally let's calculate the centripetal acceleration, and that's equal to negative 0.866 radians per second squared crossed or multiplied by the position of C with respect to B, which again is 0.8 meters in the I-hat direction. And doing the arithmetic, I come up with negative 0.6 in the I-hat direction. So what I'm going to do is equate components in both the I and the J-hat direction, just like we did with velocity. So in the I-hat direction, I've got for the acceleration of C is AC cosine 30. In the I-hat direction for AB, I've got 0.6 meters per second squared. For this cross product, alpha BC crossed with the position of C with respect to B, I don't have anything in the I-hat direction, so I'll just add a 0 there as a placeholder. And then finally, this last term, what I've got is negative 0.6 in the I-hat direction. So what this says then is 0.6 minus 0.6 is 0, and the acceleration of C is actually 0 meters per second squared. And I'll do the same thing in the j-hat direction. For AC, I'll have AC sine of 30, and that will equal for the acceleration of B in the j-hat direction, a negative 7.2. And with this cross product, I'll have in the j-hat direction now is plus 0.8 alpha BC. And finally, for this last term, I'll have in the j-hat direction, I have no components, only acting in the I-hat direction, so I'll just add a 0 to that. And since AC is 0 meters per second squared, I can solve for alpha BC. And what I'll come up with, the angular acceleration of linkage BC, I'll come up with 9 radians per second squared. So here's our final answer. The acceleration of C, there actually is no acceleration of the piston at this moment in time. And the bar is accelerating in the positive k-hat direction, or in this for a right-hand coordinate axis, it's accelerating counterclockwise.